Hello and welcome back. All right, 1.3 Illustrative Examples. Okay, yeah. So I just want to mention some of these. Um, Limit as x approaches 0 of the function 1 over x squared. And we've talked about this from a graphical point of view, but not from an analytical point of view. Let's talk about this one. Okay, so 1 over x squared. The function 1 over x squared, what does it look like? Well, if you're not sure, make a quick table, right? X, Y. Let's do first. Let's do something like let's do 1, 2, 3, 4. -1, -2, -3, -4, and then we'll do some other numbers after that. So 1 squared is 1, 1 over 1 is 1, 2 squared is 4, 1 over 4 is 1 over 4, 3 squared is 9, we get 1 over 9, 1 over 16, -1 squared, +1, -2 squared, 4, 1 over 4. So, y values are identical. That's supposed to be 1 over 16 there. So the y values stay positive, but they decrease. They get smaller as x increases. Now, what about this? What about 0 0.1, 0 0.01, 0 0.001, and therefore they're negatives, right? I'm not going to write the negatives because you can see what happens. 0.1, that's like 1 over 10, right? 1 over 10. If you square 1 over 10, you're going to get 1 over 100, and 1 over that, 1 over 1 over 100 is 100. This is 1 over 100. If you square 1 over 100, you get 1 over 10,000. And then 1 over that is going to be 10,000. Okay. Same reasoning. This is 1 over 1,000. If you square that, you're going to get 1 over, add 3 more zeros, right? 1 over 1,000,000. And then 1 over that is 1,000,000. So you see what's happening. As x gets smaller, as x approaches 0, this number, the y value, gets bigger, 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 as we can see from the table. Okay? And obviously, if you square a negative number, it becomes positive. Okay? So for that reason, without doing any graphs, we can say the limit as x approaches 0 from the left, that's the negative side. And again, if you square a negative number, it's still positive. So this is going to be positive infinity. Likewise, the limit as x approaches 0 from the right, negative infinity. Okay? So it looks like this. Going to 0 as x goes to infinity, going to infinity this way, and then over here it's just a mirror image. Okay? So that's what it looks like. I don't know why I wrote negative infinity there. Positive infinity in both cases. Okay? Positive infinity in both cases. And once again, this is a more descriptive version of does not exist. Because infinity is not a real number. This means is not an element of the real numbers. And there's the fancy R that I can't. Yeah, it's actually not too bad. So there you go. There's that. What else? We also have this one. Limit as x approaches 0 of the following. Absolute value of x over x. And what I want to do is I want to split this, like we have been. consider the left-hand limit, and then separately consider the right-hand limit. Okay. Well, if I do the left-hand limit, if I sketch from the left of 0, that means x is less than 0. Okay? In other words, x is negative. X is negative. Okay? Now, let's think about some negative numbers. What's the absolute value of negative 1? Absolute value of negative 1 is 1. Absolute value of negative 2 is 2. Absolute value of negative 3 is 3. Question. What do I multiply negative 1 by to turn it into a 1? Negative 1. What do I multiply negative 2 by to turn it into a 2? Negative 1. Right? Negative 2 times negative 1 is positive 2. What do I multiply negative 3 by to get positive 3? Once again, negative 1. Okay? So, in other words, the absolute value of x, if x is negative, is exactly negative x. Okay? So, in other words, this becomes the limit as x approaches 0 from the left, negative x over x. And now, x over x is 1, but we got a negative. So this answer is negative 1. Okay. So left-hand limit, negative 1. Now let's consider the positive case. Now the positive case is easier, right? Because the absolute value of a positive number is just itself. Absolute value of 5 is 5. Absolute value of 6 is not 5, it's 6. Absolute value of 7.8 is 7.8, so on and so forth, okay? So the absolute value of x is just x. X over x is positive 1. And now look here, right? Without doing any graphs of any sort, the left-hand limit is not the same as the right-hand limit, okay? So therefore, the limit as x approaches 0 of the function absolute value of x over x does not exist, because the left-hand limit is not the same as the right-hand limit. Right-hand limit is not the same as the left-hand limit. Let me get my eraser back out of here. There we go. They're not the same. One of them is 1, one of them is negative 1. They're not the same. There we go. Okay. Do I have my smart view? Let's see. Come on, smart view. Smart view. I hope it works. I hope my license hasn't expired. Is it gonna work? Sweet. Okay, let's take a look at that function. Okay. So what I'm gonna do is I'm gonna go to math, and I am going to have it. Oh, you can tell I haven't used absolute value in a while. There we go. Absolute value. There it is. Sweet. Absolute value of x. Okay. And then we're going to divide that by x. Okay, and we're just, we're basically checking to see if our results are correct. So left-hand limit, we should get negative 1. Right-hand limit, we should get positive 1 as we approach 0. So let's take a look and let's see if that actually happens. Let's do a zoom 6 first. To get, oh, there we go. Look at that. Look at that. Wow. Right? So we immediately see what's going on here. And this makes sense, right? Because, x over itself is just 1. Negative x over itself is negative 1. Left hand limit, negative 1. Right hand limit, positive 1. There we go. So that's what's happening there. All right, good. Let's go through. Let's go through 2 more. This one will be even faster. Limit x approaches 0. 1 over x. Okay. Compare the table to this one, and we're not going to be squaring, but we're going to be doing 1 over the number, right? So think about those small numbers, right? 1 over 0.0, 1 over 0.1, for example, is 10. 1 over 0.01 is 100. 1 over 0.001 is 1,000. So on and so forth. As you continue to add zeros in front of that 1 over that number is just going to get bigger and bigger and bigger and bigger. We're not squaring this time, so we will have negatives, right? So like 1 over negative 0.1 is negative 10. 1 over negative 0.01 is negative 100. So on and so forth. So, this function, sorry about the horrible axes there. This function, if I plot it, looks like this. This is the reciprocal function. Hopefully it's familiar from pre-cal. Looks like this. Okay. And, this is just what I was saying in graphical form. As x approaches, as x gets closer to 0, so 0.1, 0.01, 0.001, 1 over that number gets bigger. And we do the same thing from the negative side, except we're going down instead of up, right? So to distinguish this from 1 over x squared, we have limit x approaches 0 from the left. And yeah, look from the left, boom, negative infinity. Limit as x approaches 0 from the right, positive infinity. Okay, here's 0, sketching from the right. There we go, positive infinity. Okay, all right. Now, the last example I wanted to discuss is the most difficult of the examples, and that is this one. Limit as x approaches 0. And here's where stuff gets pretty crazy. The sine of 1 over x. This is bananas. Okay? So, we just talked about 1 over x. Okay, and, maybe I should have made a table before. I'll make a table now. So, first let's just look at x and 1 over x as x approaches 0. So let's think about x equals 0.1, 0.01, 0.001. Okay, that should be enough. 1 over that's going to be 10. 1 over that's going to be 100,000. 10,000. 100,000. A million. Okay. All right, so try to visualize what's going on here. As x gets smaller, okay? Let me write this down. Let's probably write some things down. As x decreases, as x decreases, to 0 from above. In other words, from a positive number, like we've done here in the table. Not y, but 1 over x increases without bound. Oh, I can't spell. Without bound. Okay. Let's consider the number of periods. Between these x values, and we're just going to estimate. Okay. So, the regular sine function, the period of the regular sine function, the period of sine x is 2 pi. Okay, so in other words, every time the x value changes by 2 pi, then the sine function completes a full cycle. It goes up and then back down, and then it returns to the y value where it started. Okay. So let's just consider the number of, because here's 1 over x. 1 over x, as x goes from 0.1 to 0.01, 1 over x goes from 10 to 100. Let's think about how many periods are in there. Well, the distance between 10 and 100 is 90, right? So if we take 90 and divide by 2 pi, 90 divided by 2 pi, 2 pi is like 6.28, right? 3.14 times. We get about 14 periods. 14 periods from x equals 0.1 to x equals 0.01. Okay? Now, let's do the next one, right? From x equals 0.1 to x equals 0.001. How many periods? Well, 1 over x goes from 100 to 1,000. So the distance there, so 1,000 minus 100, it's 900. Okay? That's how much 1 over x changes by. And now, how many periods is that, right? So let's take 900 and divide by 2 pi, right? So 900 divided by 2 pi. No. Oh, 900 divided by, and I'll actually enter it here, 2, oops, parentheses, 2 pi. 900 over 2 pi? 140, well, yeah, we could have guessed that, right? So obvious. 143 periods. From there, we get the idea, right? So, from x equal 0.001 to 0.0001, the distance is going to be 9,000, and we're going to have over 1,000 periods, right? So what's next, right? As x approaches 0, the number of periods of y equals the sine of 1 over x, the number of periods increases without bound. And this is such a good problem, honestly. This is a really good thing to analyze. Okay, so as a consequence, y equals sine of 1 over x touches every real number from -1 to 1 an infinite number of times as x approaches 0. Touches every real number from -1 to 1 an infinite number of times as x approaches 0. Okay. And so if you're not careful, you can make it appear for this reason. This is why you can make it appear that the limit as x approaches 0 of the sine of 1 over x equals r, where r is any number between -1 and 1, because it touches every number an infinite number of times. If you're not careful, you can make it look like the limit is any one of these numbers. And the fact that you're able to do that, first of all, is quite remarkable. But it shows that the limit cannot be any one particular value. And so because the oscillations never stop, spell check, I feel like maybe I spelled that one wrong. Because the oscillations never stop, the limit as x approaches 0 of the sine of 1 over x does not exist. Okay. Oscillations never stop. There's no convergence. And if I try and plot this, you can see what I'm talking about. Sine, make sure I'm in radians, yeah. The sine of 1 over x. And I'm going to do a zoom 6 first. And yeah, it looks kind of squiggly. Let's do a zoom 4. Okay. See, there's so much going on in this region that it's basically ignoring all the processing. So we're going to be really mean to this thing. We're going to go, like, let's try -1 to 1 on the x min and max. And then for the y min and y max, because this is a sine function, we know that the max and min are going to be -1. So let's go -1.1 so we can really see what's going on. And then 1.1. Okay? And let's graph. And look at that. Look at that, right? So you can see, as we're coming in, the number of periods increases. Okay. Um, let's be meaner, right? Negative 0.1 to 0.1. Let's graph it. Look at all that. As I zoom in further, we're going to see more and more periods. This oscillating is never going to stop for the reasons that we've already outlined. Let's throw some more zeros here. Negative 0.00. Yeah. There we go. This is point. Okay, yeah, let's graph it. Look at that. Look at that. It just gets worse and worse and worse and worse. Right? So we are the point is that no matter how much you zoom in, let's do one more. I'm trying to show you that it gets worse as you do this. Graph it. Look at that. No matter how much you zoom in, these oscillations are never going to stop. This thing is never going to converge to a single number. So the limit doesn't exist for that reason. Okay. Great. So yeah, that I think we've covered pretty in detail basically every reason why a limit can't exist. Awesome. All right.